Hello again, and welcome to our lecture on rational functions. You'll remember that a rational number, or a fraction, is a quotient of two integers, like 2 over 3, 2/3. Well, a rational function is a quotient of two polynomials. For instance, the rational function f of x equals x squared plus 4 over x cubed minus 1 is a quotient of two polynomials, and that's an example of a rational function. And today we'll talk about rational functions, and some of the key issues will be issues we brought up before with functions. What are the domains of these rational functions? What do their graphs look like? And of course, let's see some applications of rational functions. So the formal definition of rational function is basically what I just said. It's a function that can be written as a quotient n of x over d of x, where n and d are both polynomials. And the domain of a rational function consists of all x values for which the denominator is not 0. Because remember, you can't divide by 0 in math. So if the denominator is 0 for some x value, that's not going to be in the domain. And let me also make another quick comment. We aren't going to use complex numbers in this lecture or for the remaining, say, 10 or 20 lectures. So we'll put the complex numbers behind us for a while. They'll come in later on in the course. So what's a rational function look like? What's the graph of a rational function? What attributes does it have? Well, let's look at perhaps the simplest example of a rational function, f of x equals 1 over x. And let's ask some good questions. What's the domain? Well, clearly x cannot be 0. So the domain is all real numbers except for 0. Now look what happens here when we approach 0 from the right. As we get towards 0 from the right, as x gets nearer and nearer to 0, 1 over x gets bigger and bigger. 1 over a small number is a large number. So what we say is that as we approach 0 from the right, the function increases without bound. In a similar manner, as we approach from the left, the function decreases without bound. Now here's another interesting feature of this function. What happens as x gets very large? What happens if x is, say, 1,000,000 or minus 1,000,000? Well, I think you see that 1 over a very large number is very close to 0. So we can sort of see this behavior getting close to 0 and when x is large on either side. And then by plotting a few points like 1, 1 or -1, -1, we obtain the following graph. This is the graph of the rational function 1 over x. It has some very interesting features, I think. First of all, the y-axis, x equals 0, is a vertical asymptote. And the x-axis is a horizontal asymptote. And you also see that this is an odd function. It's symmetric about the origin. So again, x equals 0 is called a vertical asymptote, and y equals 0 is called a horizontal asymptote. And the idea of asymptote technically involves something called limits. It's the behavior as you get closer and closer to a number, or as x gets really, really large. Limits is a big topic in calculus classes, but I think we can understand this asymptotic behavior even in a pre-calculus course. What we're saying is that, for instance, as x gets very, very large, positive, then 1 over x is getting closer and closer to 0. Good. Let's look at a slightly more difficult example. Let's find the vertical and horizontal asymptotes of the rational function 2x divided by 3x squared plus 1. Here's a picture of that function. And it doesn't look like it has a vertical asymptote, but it does seem to have a horizontal asymptote being the x-axis. Well, it doesn't have a vertical asymptote because the denominator is never 0. The domain of this function is all real numbers, so we don't have to worry about division by 0. But the horizontal asymptote, you can see in an intuitive way that as x gets very large positive, the numerator is 2 times a large number, but the denominator is 3 times a large number squared, and hence the denominator kind of overwhelms the numerator and the quotient approaches 0. All right, here's a similar looking example, but I've made it even more interesting. 2x squared over x squared minus 1. What are the asymptotes, domain, etc.? Well, clearly, if x is 1 or minus 1, you're dividing by 0, and hence the domain is all real numbers except for plus and minus 1. And in fact, x equals 1 and x equals minus 1 are vertical asymptotes. As x gets closer and closer to 1 or closer and closer to minus 1, the function gets very, very large or very, very small. And furthermore, there's a horizontal asymptote at y equals 2. Here's how you can see that. It's 2x squared divided by x squared minus 1. When x is really large, that minus 1 becomes irrelevant. And it's really 2x squared divided by x squared. They're both going to infinity. I admit that. But the top one is twice the bottom one. So you see that the horizontal asymptote is y equals 2. Here's a picture of that graph. Kind of difficult, I think, to draw that graph by hand. But with a graphing calculator, you can produce this graph, and I invite you to do so. Notice that the has 2 vertical asymptotes at 1 and minus 1, and then you see that horizontal asymptote at 2. Interesting looking function, I think. Now, rational functions have lots and lots of applications. Let me pause here real quickly and show you one from chemistry. We won't delve into this application too much, but if you studied chemistry, you probably remember Boyle's law. And let me remind you what it says. Boyle's law says that for a quantity of gas at constant temperature, the pressure is inversely proportional to the volume. And you can write that as the following equation. P, pressure, equals K over V. V's the volume, and K is a constant of proportionality. And there are some units involved here, but I won't worry about those. But P is now a rational function of the variable V. So you could ask yourself, what happens to the pressure P when the volume approaches 0, when you squeeze in this volume? Well, I think you see, according to the equation, that when V gets near 0, P gets bigger and bigger. The pressure gets larger and larger. Okay. Let's take it up a notch. Let's look at a trickier example. Vertical asymptotes have a little bit more to worry about here. Here's a function, x squared minus 4 over x minus 2. It's a rational function. The domain is clearly all x except for 2. What are the vertical asymptotes? Well, you might think x equals 2 because the denominator vanishes at 2. But wait, watch what we're going to do here. Let's take the numerator and factor it. So it becomes x plus 2 times x minus 2 divided by x minus 2. And then we see the common factor x minus 2. So we cancel those common factors. And this original rational function can be simplified to x plus 2, the surviving factor in the numerator, as long as we remember, be careful here, as long as we remember that x cannot equal 2. X cannot be 2 because 2's not even in the domain. So what do we have here? This rational function looks like the line x plus 2, doesn't it? That's a straight line, except wait, it's got a hole in it. There's a hole when x is 2. So this is what I like to call, when I'm teaching pre-calculus or calculus, the proverbial line with a hole in it. And the hole is at x equals 2. This kind of function, where you have this cancellation and you get curves or lines with holes in them, occur quite a bit in calculus courses. In summary, this function, this rational function, doesn't have any vertical or horizontal asymptotes. It doesn't. It's really a straight line, but with a hole in it. Kind of neat. It's the straight line x plus 2, slope 1, y-intercept 2, but when x is 2, It's got a hole there. In fact, it wants to be 4, doesn't it? If you wanted to fill in that hole with some chalk, you would fill it in at 2, 4. But 2 is not in the domain, so you can't fill it in. So this brings up a general pitfall that I can't help but reiterate again. You can't just look at the denominator to determine the vertical asymptotes. Just because the denominator is 0 doesn't mean you necessarily have a vertical asymptote there. Let me show you another tricky example. Look at the following kind of complicated rational function. The numerator is x squared plus x minus 2. The denominator I'll factor for you, x plus 2 times x minus 3. And I ask you, what are the vertical asymptotes? And you might automatically say, well, minus 2 and 3, because that's where the denominator vanishes. But I'm tricking you. Factor that numerator. It factors to x plus 2 times x minus 1. Common factor of x plus 2. Cancel that common factor, and we have a new version of our rational function. It's x minus 1 over x minus 3, as long as we remember that x cannot be minus 2. Minus 2 is not in the domain of this function. So, what's happening here? Well, look at the graph, and you'll see what happened. We only have one vertical asymptote, and that occurs at x equals 3. Over there at minus 2, there was not a vertical asymptote after all. There was a hole in the graph. And in fact, as we'll see in a few minutes, that hole occurs at minus 2 comma 3/5. That's where the hole is on the graph. So this complicated rational function simplifies slightly to another rational function with one vertical asymptote, a hole, and of course it has a horizontal asymptote at 1, y equals 1. Okay, good going. I think you can see that graphing these rational functions is a non-trivial task. And when you take a calculus class, you'll learn many advanced techniques for graphing functions. The good news is in today's world, we have these graphing calculators and computers that can produce graphs very quickly for complicated functions. I invite you throughout this course, when you see one of our pictures, try to replicate it with your own graphing calculator. It's kind of nice to say, hey, I got the same graph as on the DVD. Let me ask you some questions now that we're experts on asymptotes. How many vertical asymptotes can a graph of a rational function have? How many? Well, I say it can have any finite number. Like, the number depends on the polynomial in the denominator, doesn't it? And if that's an nth degree polynomial, then it'll have up to n vertical asymptotes. That said, there are functions that have an infinite number of vertical asymptotes. In fact, when we study trigonometry, we'll see such a function. Okay, here's a similar question. How many horizontal asymptotes can a rational function have? And the answer here is a little bit easier. It can be 0, and we've seen an example of that, like a straight line, or it could have 1. Now, there are functions out there that are not rational that have 2 horizontal asymptotes, one to the left and one to the right. And we'll see an example of that in a moment. Okay, before we look at that example, I'd like to sort of summarize how to handle horizontal asymptotes for rational functions. The bottom line is there's sort of 3 cases. A rational function can have a horizontal asymptote at 0, the x-axis, or it could have a horizontal asymptote, say at some positive or negative number, or it might not have a horizontal asymptote at all. So let's look at these 3 cases. Here's the graph of the function 2x over 3x squared plus 1. This graph has a horizontal asymptote at y equals 0. And here's the intuitive reason why. The numerator is 2x, but the denominator is 3x squared plus 1. As x gets really large, either positive or negative, the denominator will overwhelm the numerator, and hence the quotient approaches 0. Well, here's a related function, 2x squared over 3x squared plus 1. The only change now is the numerator is 2x squared. What's the situation now? Well, now it has a horizontal asymptote at 2/3, at y equals 2/3. Now, why is that true? Well, do the same informal argument. The numerator is 2x squared, the denominator is 3x squared, and when x is large, you can ignore that plus 1. And it's something x squared divided by something else x squared. The leading coefficients, 2/3, determine that horizontal asymptote. And a third example, related to the first two, now I'll change the numerator to 2x cubed. And now the numerator is bigger than the denominator, and hence this function doesn't have a horizontal asymptote at all. As x gets very large, the numerator overwhelms the denominator. Now, a lot of people might say, that was a very good informal argument about asymptotes, Professor. I want to see an algebraic argument. So let me look at that first example we did, 2x over 3x squared plus 1. And let me try to convince you why the horizontal asymptote is y equals 0. And here's how the analysis goes. And this same analysis would work for any rational function. Take your given function, 2x over 3x squared plus 1, and multiply numerator and denominator by 1 over x squared. You'll see why in a minute, the reason for doing this. What happens to the numerator? 2x times 1 over x squared is just 2 over x. And the denominator becomes 3x squared times 1 over x squared, so that's just 3, and then plus 1 over x squared. So we've rewritten the rational function in a new form, but this form is easier to understand because look, when x goes to infinity or to minus infinity, when x gets really, really big, like a billion, the 2 over x and the 1 over x squared die off. They approach 0. And you're left with 0 in the numerator and 3 in the denominator. And hence the quotient is 0. So the limit is 0 as x gets larger and larger. And you can do this analysis with the other two examples I gave you. So what's the summary of our rules for horizontal asymptotes of rational functions? If the degree of the numerator is less than the degree of the denominator, y equals 0 is a horizontal asymptote. If the degrees are the same, then the horizontal asymptote is given by the ratio of the leading coefficients, in that example, 2 over 3. And if the numerator has a greater degree than the denominator, then there's no horizontal asymptote. Now, I promised to show you a function that has two horizontal asymptotes. Let me show you this function. It's kind of an interesting function. It's kind of bizarre. It's not a rational function. And of course, there are many such examples, but I chose this one. Let's consider the function x plus 10 divided by the absolute value of x plus 2. It's not a rational function because that denominator is not really a polynomial. It's got that absolute value sign in there. And if you're like me, you get a little nervous when you see absolute value signs, like, oh, I don't like to deal with those. So I recommend you consider the two cases, when x is positive and when x is negative, and that'll let you analyze that absolute value function. So when x is negative, the absolute value of x is minus x. So for negative x, the function equals x plus 10 over minus x plus 2. Whereas if x is positive or is equal to 0, then the denominator is just x plus 2. So we've expressed this unusual function, this non-rational function, in terms of two rules. When x is less than 0, do this rule, and when x is greater than 0, do the other rule. Now look what happens. Look at these two rules. When x is less than 0, say going to minus infinity, the quotient of the leading coefficients is 1 over minus 1, so it has a horizontal asymptote of minus 1 to the left. But to the right, the horizontal asymptote is 1 because the quotient of x plus 10 over x plus 2, the leading coefficients are 1 over 1 or 1. Here's a picture of that unusual function. And you can see that it has two horizontal asymptotes. Its horizontal asymptote to the right is 1, and to the left is minus 1. Okay, that was a tricky example, and it wasn't really a rational function, but kind of a fun example. Let's turn to an application. Suppose you're designing a school poster, and you'd like this poster, say, to have 48 square inches of printed material, maybe a picture and some words. But you also want to have some margins, both on the left and the right and on the top and the bottom. And let's assume the margins on each side, on the left and the right, are 1.5 inches. And then on the top and the bottom, let's say 1 inch. So it's 48 square inches of printed material, and then you have these margins, 1.5 inches on either side, 1 inch on the top and the bottom. Here's a picture of the setup. Here is a picture of our proposed poster, and I've labeled the dimensions of the printed part x by y. X is the horizontal distance, y is that vertical distance. And then you see that I've added 1.5 inches on either side, those are the margins, and then 1 inch on the top and the bottom. So the question is, what should the dimensions of this poster be in order to minimize the amount of paper used? We want to save money. I want the smallest amount of paper to be used to construct this poster under these conditions. Okay, let's get to work. We've labeled the dimensions of the printed part as x and y, and because that has to be 48 square inches, we know that x times y is 48, and then we can solve for either variable, like y is then 48 over x. So, what's the area to be minimized? Well, it's the larger area, the whole paper. So that's, this way, it's x plus the two margins. And the margins were 1.5, so it's x plus 3, 1.5 on each side. And how about this way? It's y plus the margin of 1 and the margin of 1, so it's y plus 2. So we want to minimize the quantity x plus 3 times y plus 2. But we know what y is. We can replace y with 48 over x. So we have a new function, the area equals x plus 3 times the quantity, 48 over x plus 2. And we can do a quick simplification, get a common denominator, and it's x plus 3 times 48 plus 2x, all divided by x. Okay, we want to minimize this function. Ouch, not clear how to do it. Now, if you took a calculus class, you would learn some skills to find the minimum value of this function. But we have graphing calculators. We could graph this function. It'll have an unusual looking graph. And then we can find the minimum value. Remember, we're trying to find the values of x and y that make the area of the big piece of paper, the poster, as small as possible. Well, here's the graph, using a graphing calculator, of our area function, x plus 3 times 48 plus 2x, all divided by x. Wow, kind of an interesting looking graph, isn't it? It seems to have a vertical asymptote over there when x is 0, and indeed it does, because x equals 0 is a vertical asymptote. And then it seems to have a minimum point, and then the graph grows again. Okay. What's that minimum value? Well, your graphing utility has a button on it which allows you to find or approximate the minimum value of a graph You can actually zoom in on that bottom part of the graph and discover the minimum value. It turns out that x is approximately 8.5 at the low point of the graph. And when x is approximately 8.5, the y value, 48 divided by 8.5, is about 5.6. So those are the x and y values. Remember, the paper was bigger, so we have to add the margins. X plus 3 is 11.5 approximately, and y plus 2 is approximately 7.6. Those are the dimensions to minimize the amount of paper. And as I said, if you took a calculus class, and I hope you do, after you take this pre-calculus course, you'll be ready for calculus, you'll discover a technique for finding the exact value of that minimum. And it turns out to be 6 square roots of 2. That's the precise answer. And that's about 8.485. Okay, why don't you be the teacher again? This is kind of fun to do. You're making up yet another test. And this time, you want to have a rational function with certain properties. You want the asymptotes to be, the vertical asymptotes, to be at -2 and at 1. You'd like it to have a horizontal asymptote at y equals 2. And how about zeros at x equals 3 and -3? What should your function look like? Well, let's build it. It has zeros at 3 and -3. So in the numerator, we have to have an x minus 3 and an x plus 3. We want those vertical asymptotes at -2 and at 1, so the denominator needs to have an x plus 2 and an x minus 1. Now there's one more feature, horizontal asymptote at 2, y equals 2. Remember, that's the quotient of the leading coefficients, so I'm going to have to add a 2 in the numerator to make that quotient 2. So multiply out this kind of frightening looking expression, and you get your function to be 2x squared minus 18 over x squared plus x minus 2. So you're the teacher. Here's what you do. You tell the student, or you ask the students on a test, dear students, here's a problem. 2x squared minus 18 over x squared plus x minus 2. I want you to find the vertical asymptotes, the horizontal asymptote, and the zeros. Tough question, but we know how to do it because we sort of did it backwards. Okay. Let's do some true-false problems. I don't think we've done any true-false problems. I like to put these on tests, the main reason being they're easy to grade. So here are some true-false questions. First one, a rational function can have infinitely many vertical asymptotes. Well, the answer is false. Remember that the number of vertical asymptotes is related to the degree of the polynomial in the denominator. That said, again, tune in for trigonometry when we'll see the tangent function and some others that have an infinite number of vertical asymptotes. Okay, so that was a false. Another question. A rational function must have at least one vertical asymptote. What do you think? False again. For instance, 2x over 3x squared plus 1, an example we've seen earlier today, doesn't have any vertical asymptotes. The reason being the denominator is never 0. 3x squared plus 1 is always positive. So that's false too. A third question. The graph of a rational function can cross a horizontal asymptote. Can you cross your horizontal asymptote? And the answer is true. And in fact, if you look at that previous example, 2x over 3x squared plus 1, you'll see that it crosses the horizontal asymptote at the origin. Another question. Can the graph of a rational function cross a vertical asymptote? And the answer here is false. It cannot, because the vertical asymptotes come about where the denominator vanishes, and those points are not in the domain of the function. Great going. I hope you've enjoyed this very brief study of rational functions and some simple applications. So what's next? What are we going to do next time? Well, we'll turn now to a topic called inverse functions. Again, a big topic in pre-calculus and a major role in calculus. Let me give you a taste of what we'll do. Here's some simple examples. The function 5x multiplies x by 5. Its inverse is x divided by 5. They kind of undo each other. First you multiply by 5, and then you divide by 5. You're back to where you started from. Or how about x cubed? Well, it's the inverse of the cube root function. They undo each other. Now, these inverse functions will play a major role when we get to the exponential function, because its inverse will be the logarithmic function. And then we'll study trigonometry, and we'll have the trigonometric functions, and then we'll develop their inverses. So there's a lot of power in these inverse functions, and we'll touch on that topic next time. I'll see you then.